Hello, my name is Hassan Lakis. Welcome to this tutorial in which I'm going to have a look at the first three derivatives, in particular to show or demonstrate that at the local maximum the second derivative is negative, and at the local minimum it is positive, and we'll have a look at a point of inflection. I've already set up my axis. I've chosen advanced mode, chosen degree, chosen equal aspect, and I just want to show you that I already typed my equation, but the way I did it was pressed enter, or you go to equation and select enter equation. My advice is, before you do that, select the slope plot so you can discuss the points of intersection with the axis before you actually do what I've just done. So if I click that and I double click that to show you, that's what would happen, and then you press OK, and you can pause and discuss where it intersects the axes, which way it's going up, and there we go. Okay, what we're going to do is ask Autograph to draw the gradient function, or they call it slope function, of this cubic. So you select it with the left mouse, and the slope plot is on, so you can pause it if you want to. Select slope function, and it's going to plot dy by dx against x at various points around the curve and give you the function. It will pause at stationary points, and that's one of them there. Dy by dx is 0. Click that button there, and it stops at that point here, somewhere where there's a point of inflection, and again at the local minimum, and so on. So we get a quadratic function, and it could easily expand the brackets out and differentiate it. I'm thinking about the core unit C2 at Excel, A-level mathematics, or AS. Now, if we select that, the new derivative, and go slope function, it will now plot d2y by dx squared against x. Again, it'll stop at any stationary points, and it'll stop at this point down here because of the point of inflection. Continue, and we get a straight line graph, and that could also be found by finding the second derivative. What I'm interested in is looking at this local maximum point, and if I come down to the x-axis, that's the x value roughly here. If I go down and substitute that into my second derivative, I'll see that the y value is negative, meaning that d2y by dx squared is negative, because that's represented by this straight line here. And at this point here, the local minimum, the x value substituted into the equation of the second order derivative, you can see it's positive as you come up here. And if we want the third derivative, we select that and go gradient function. Okay. You can see it coming through here at 6. Just press the pause button and it continues. Okay. Now, next I would like to put in an equation, enter an equation, a cubic with a point of inflection. So if I go to equation, or just press enter and type in y equals something like 2 minus x cubed, and let's say plus 1 to keep it away from the x-axis, and there we go. If at any time you want to plot it quickly, then you simply click the slope plot. It will do that for you. So there it is. If I just remove this one here backspace, remove that one, backspace. Then I'm left with two curves. Now if I select that one and go gradient function, we know there's a dy by dx is 0 here, and it's a point of inflection because we can see it. It should pause at that point and show you that dy by dx is 0. There we go. So the first derivative is 0. Continue, and there it is. And of course, if we I'm just double clicking that so you can see the equation. If we differentiate that, we're going to get minus 3 brackets 2 minus x all squared. So the quadratic is negative, and that's why you're getting this. I'll just cancel that. Now if I select that and go gradient function again, so that's the first derivative, dy by dx plotted against x for that blue, the cubic that I've just drawn, and it'll stop again there, and there we go. And you can see it's a straight line with a negative slope. So if I did say that if we differentiate this function, first derivative, we're going to get minus 3 brackets 2 minus x all squared. If we differentiate again, what do we get? We get a straight line with a negative gradient, which is this green one here. It's just replotting that cubic because I didn't press cancel. Okay, so you can see clearly that first of all dy by dx was 0 at this point here, which is in fact the x value for the turning point, obvious from the equation of the cubic. And if I select that and go gradient function for the third derivative, we should get a straight line which is at minus 6, and you can see it coming out. And to make it quick, I'll just press the slope plot. There we go. So it's at minus 6. So if you differentiate the third time, you're going to get minus 6. So what happens when x is 2 and you substitute that into d2y by dx squared, you're going to get 0. So in the normal circumstance, if we haven't got a graph in front of us, we will say that it's inconclusive as to whether it's a local maximum or minimum or a point of inflection. We can then differentiate again, and if the third derivative is positive or negative in some cases, then it is a point of inflection. Or we can always go back and have a look on either side of dy by dx, the x value I mean, and substitute into dy by dx. If there's no sign change in dy by dx, then we know it's a point of inflection, and I'm sure you know all that. That's all I have time for. I hope you found it useful. Until the next video, take care.